In this module, we will explore system threats, specifically focusing on understanding denial of service, often called as DoS, and buffer overflow attacks. Denial of service attacks aim to make a system unavailable, while buffer overflows exploit vulnerabilities in memory management. Let's delve into each of these threats in detail. Let's begin by understanding denial of service attacks. A denial of service attack is a deliberate attempt to make a system or network resource unavailable to its intended users. This is often achieved by overwhelming the target with an excessive amount of requests or traffic, effectively preventing legitimate users from accessing the services. Common DoS methods include flooding attacks, such as SYN, User Datagram Protocol, also called as UDP, and Internet Control Message Protocol, also called as ICMP floods. Application layer attacks target specific vulnerabilities in applications. Also, distributed denial of service or DDoS attacks, which utilize botnets to amplify the scale of the attack. Now, let's focus on distributed denial of service attacks. In a DDoS attack, multiple compromised systems forming a botnet are used to launch the attack. This amplifies the attack power exponentially, making it harder to mitigate compared to single-source DoS attacks. DDoS attacks can generate massive traffic volumes, often exceeding 100 gigabits per second. Attackers frequently use reflection techniques to hide the true origin of the attack, further complicating the defense efforts. To defend against DoS attacks, several mitigation strategies can be employed. Traffic filtering and rate limiting can help to block or throttle malicious traffic. Load balancing distributes traffic across multiple servers to prevent any single server from being overwhelmed. Implementing a content delivery network or CDN can also aid in traffic distribution and reduce the impact on the origin server. Black hole routing involves directing malicious traffic to a null route, effectively dropping the traffic. Here is a basic rate limiting middleware example. The function rate limit takes max requests and time window as parameters. It returns a function that takes a request, a response, and next as parameters. Inside this function, a new map called clients is defined. The function returns another function that defines client IP as request.ip, and now as date.now. If the client IP does not exist in clients, then the client IP is added to the clients. The client requests are extracted from the clients. Then rate limiting logic is implemented. Let's shift our focus to buffer overflow attacks. A buffer overflow occurs when a program writes data beyond the allocated boundaries of a buffer. This overwrites adjacent memory locations, potentially corrupting data, crashing programs, or even executing malicious code. Buffer overflows exploit poor memory management practices in applications. To understand this better, consider a typical process memory organization. It includes sections like stack, heap, data, and text. Stack is used for local variables, function parameters, and return addresses. Heap is used for dynamically allocated memory. Data is used for global and static variables. Text is used for the program code, which is read-only. A reserved section is there for the operating system kernel space. A stack-based buffer overflow is a common type of buffer overflow attack. Here's an example of vulnerable code. The C program has a function named vulnerable_function, which takes a character pointer called input as an argument. Inside the function, a character array named buffer is defined with a size of 64 bytes. The function then uses the strcpy function to copy the contents of the input to the buffer. The strcpy function is known to be unsafe because it does not perform bounds checking, leading to a buffer overflow if the input is larger than 64 bytes. The main function calls the vulnerable function with a command line argument. When a buffer overflow occurs, the stack memory layout is compromised. When buffer overflow occurs, the function arguments, return address, saved frame pointer, local variables, and other stack data are affected. Return address gets overwritten. The buffer overflow attack execution involves a series of steps. First, the attacker identifies a vulnerable program with an unchecked buffer. Then, the attacker crafts an input larger than the buffer size. The input includes shellcode, which is a small piece of code that the attacker wants to execute on the system. Next, the attacker overwrites the return address on the stack to point to the shellcode. When the function returns, it jumps to the shellcode instead of returning to its caller. Common attack targets includes network services and daemons, command line utilities with user input, web applications with native components, legacy systems with outdated security, and Internet of Things devices with limited memory protection. To prevent buffer overflows, defensive programming practices and system-level protections are essential. Here's an example. Instead of strcpy, strncpy is used, which takes the size of the buffer as the third argument, which ensures that no more than size of buffer -1 characters are copied to the buffer, preventing the buffer overflow. Then buffer at the position of size of buffer -1 is set to null to ensure null termination. The other function modern _ function takes a character pointer as an argument. Inside the function, the synprint function is used to copy input to the buffer. Synprint prevents buffer overflows because it takes the size of the buffer as an argument, which ensures that no more than the size of the buffer number of bytes are written to the buffer. System-level protections such as address space layout randomization, also known as ASLR data execution prevention, also known as DEP or NX stack canaries, and relocation read-only, also known as RELRO, can help to mitigate buffer overflow attacks. In addition to that, compiler security flags and sanitizers can be used. In summary, let's recap the key points about system threats. Denial of service attacks prevents legitimate access to services. Distributed denial of service attacks uses multiple compromised systems to amplify the attack. Mitigation requires traffic filtering, load balancing, and rate limiting. Buffer overflow exploits poor memory management and can lead to arbitrary code execution. Prevention through bounds checking, safe functions, and system protections is vital. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.